Hi guys, you're welcome to Halogeneous Ideas. In this tutorial, we are going to be talking about information representation. We are going to be talking about the classes of information, how we can classify information, then the representation of characters, numbers, and we talk about these four representations of numbers. We talk about conversions of numbers from one type of representation to the other one. Then we have the floating point number representation. We have computer arithmetic to talk about. Then we are going to be talking about the binary coded decimal. Okay, so yeah, let's get into it. The first one, introduction. Computers can be used to store and manage data and information, which can be numbers, alphabet, or alphanumeric. Alphanumeric basically is talking about a combination of both numbers and alphabets. All right. So now, talking of binary is a concept that you need to understand if at all you want to talk about information representation, because what the computer understands on the long run is zeros and ones. So binary is a base 2 numerical system, meaning it uses only two digits, 0 and 1. Alright? The term bits is short for binary digits. Okay, it can be 0 or 1. So it is the fundamental unit of information in computing and can represent either a 0 or a 1. Binary digits are used to represent information in computers where data is stored and processed in the form of a binary code. Okay, so decimal numbers can be converted to binary by repeatedly dividing by 2. Decimal numbers are numbers in base 10. Then and noting the remainders. The process results in a binary representation of the decimal number. This process we are going to be looking into it. Then bytes, which are commonly used units of digital information, consist of 8 bits, meaning that 8 bits will make up a byte. Now, a byte can represent 256 different values. Okay, so ranging from 0 to 225. In a computer, the individual storage elements are arranged in groups called words. A word refers to a fixed size group of binary digits that a computer central processing unit can process as a unit. Okay, the group of binary digits that can be processed at once, that is what you refer to as a word. So how can we classify information that can be stored to the computer? The first one is the numeric classification, under which we have numbers. Okay, the type of data that you can execute arithmetic operation on, you refer to them as numbers. And under numbers, we have two types: the numbers that doesn't have any decimal point. Then we have the ones that have decimal points. Okay, so these ones, they don't have any decimal point, but this other one, they have decimal point, the one we refer to as floating point data. So this is real and this is integers. Okay, then we have the alphabets, which are letters basically. Then we have the alphanumeric, which is a combination of both numeric data and alphabets. So how do we represent characters in the computer? So character representation in a computer system involves assigning binary codes to characters for storage and processing. Okay, so two historical character encoding systems, including the ASCII, which is the American Standard Code for Information Interchange, and the EBCDIC, which each with its own characteristics. So the first one is the ASCII. This is a widely used character encoding standard developed in the early days of computing. It was initially designed for English and uses 7 bits to represent 128 different characters, but in the case of the EBCDIC, it uses all the 8 bits. So for ASCII, for the character set, ASCII includes characters such as letters, uppercase and lowercase, digits, punctuation marks, control characters like new line, carriage return, new tab, and we also have the special symbols that um, he, he has. So we also have the encoding scheme. So each character is represented by a unique 7-bit binary code. Extended ASCII uses 8 bits, which is 1 byte, allowing for 256 different characters with the extra bits often used to represent characters from other languages or additional symbols. So, as for compatibility, ASCII is the basis for many character encoding and is widely supported across different systems and programming languages. The first 128 characters of Unicode are identical to ASCII, making it backward compatible. Alright. So we have the EBDIC, which is another character encoding system developed by IBM for its mainframe computers. Unlike ASCII, which was designed for compatibility with teleprinters, EBCDIC was designed punch cards for punch cards. So as for the character sets, they include characters such as letters, symbols, and digits, but its encoding differs from ASCII. It also includes some specific control characters for mainframe operations. Then, as for the encoding scheme, they use 8 bits, like I said, for each character, providing a larger character set compared to ASCII. The extra bits allow for the inclusion of additional characters and symbols relevant to early mainframe computing. As for the usage, it was primarily used in IBM mainframes and associated systems. So over time, it went into extinction, and ASCII and Unicode are more prevalent in modern computing environments. So as for the incompatibility, ASCII and EBCDIC are not directly compatible. Systems using one encoding cannot interpret characters encoded in the other one. Okay, so understanding these two is particularly relevant for dealing with legacy systems or when data interchange between systems with different encoding standards is necessary. So while ASCII is more widespread today, EBCDIC was historically significant in the context of mainframe computing, especially within the IBM environment. So let's talk about how numbers are represented. The representations of numbers in a computer involves encoding numeric values into binary form, allowing computers to store, process, and manipulate numeric data more efficiently. So these are some key points about the representation of numbers. So we have the binary representation. Computers use the binary numeral system, which is base 2, to represent numbers. In binary, each digit can have a value of 0 or 1, and it has a carrying factor of 2. It has a carrying factor of 2. So I will explain this carrying factor when we want to work on an example. So we have the bit and the byte as well. A binary digit is called a bit. 8 bits form a byte. The size of the representation in bits or bytes affects the range of values that it can represent. So we have the numeric systems. Apart from binary, we have the octal, the hexadecimal, that are also used for human readability and compact representation, especially in programming. So we also have the decimal to binary conversion, which converting a decimal number to binary involves dividing the number by 2 repeatedly. Okay, we are going to take a look at 3 examples of this. So, fixed point and floating point. Numbers can be represented as fixed point or floating point. Fixed point uses a fixed number of binary digits for the integer and the fractional parts. Floating point allows for dynamic range by representing numbers as a sign, mantissa, and exponent. So, we have the integers and the real numbers. Integers are whole numbers, while real numbers include fractions. If you remember the type of yes, this, you see, the integers and the real numbers. Like what I said, integers are numbers without any decimal points, while real numbers are numbers with decimal points. So let me go back. Okay, so floating point allows for dynamic range by representing numbers as a sign, mantissa, and exponent. Okay, this is where I was. Integer representation is straightforward, while real numbers require additional considerations for precision and range. So we also have the two's complement for signed integers. Computers often use two's complement to represent signed integers. This allows for representation of both positive and negative numbers using the same set of binary codes. We also have the overflow and the underflow. Limited bit sizes for number representation can lead to an overflow when the result is too large. or underflow when the result is too small. So this can affect the accuracy of your computation. So understanding the representation of numbers is fundamental in computer science and programming as it impacts the accuracy of calculations, memory usage, and the overall performance of computational systems. Okay, so below is a representation of numbers 1 to 40 in decimal, binary, octal, and hexadecimal number systems. So for the decimal, if you have one, for the binary, you're going to be having one as well. If you have two, don't forget, we said that in the binary system, you can only have zeros and ones. All right. So instead of two in this place, it is going to be 1 0. All right. Then for the three, you are just going to be increasing this by one, making 1 1. For number four, you are going to be having, just add one to this one. Now, if I add one to this one now, I'm going to be having, normally in base 10, I'm going to be having two. Okay, but I cannot have two under binary. So basically, I'm going to be having a carrying factor of two. So that is where this zero is going to be coming from. Then I'm going to be doing um the two that I took from here. The two that I took from here, the carrying factor. If I add it to this one, I think I must have miscalculated something. If I add one to this one, it's going to be giving me 10. So I have yes, very good. So this is, I'll write my zero. I'll carry one. So one plus one is going to be giving me another 10, which is 1 0, not 10. It should be 1 0 since it's in binary. So but I cannot write the 1 0. I'll just write zero again. Then I'll carry one. After carrying the one plus zero is going to be giving me one. That is why I'm having 100 here. So just keep adding one as needed. In the case of the octal, which is the base 8, you just read 1, 2, 3, 4, 5, 6, 7. Normally, you're supposed to have 8, like what we have here, but you cannot have 8 in the octal system. So from 7, you're going to be having 1 0. Then you have 1 1, 1 2, 1 3, 1 4. Then when you get to 7, 1 7 again, you get to 2 and 0. So that is how the octal system works. But for the hexadecimal, you are going to 16. So when you get to 1, 2, 3, 4, 5, 6, 7, 8, when you get to 9, you start counting A to F. Then when you get to F, you have your 1 0. Alright? Basically, the decimal is in base 10. This is in base 2. This is the octal system that is in base 8, while hexadecimal is in base 16, and everything continues like that. And everything continues like that. So if you want more explanation on the binary systems, please just put it in the comments. I'll try to look for a writing material, something to illustrate better. If you need something like that, please just respond in the comment section. So now note, binary numbers are represented with specs for better readability. Okay, it's just, you don't necessarily have to add these trailing zeros for now. I'm just trying to make everything more readable. That's why I added it. So now the ASCII representation of characters. The ASCII representation of characters. So I came up with this. I saw this online, so I brought it up. So we have the decimal, the hexadecimal, then the character. If you come down to, okay, you can see 48 over here. So if the computer wants to represent the character 0 in memory, basically the ASCII value is 48. It will just convert this 48 to binary, and that binary, the binary equivalent is what is going to be storing this 0 as. If you come to 65, you have capital A. It will just convert this 65 to binary, and that is what is going to be the representation for A. Alright. If you want to represent K, for example, if you come here to K, you are saying that K is 107. It will just convert 107 to binary, then that will be the representation for K. So let's move on. Now, talking about conversion of numbers. The first one that we are going to be talking about is conversion from decimal to binary. So converting a decimal number to binary involves representing the decimal value using the binary numeral system. Okay, just like what I was saying here, this is the decimal. If I want to represent this plus character, for example, it is 43. I'll just convert 43 to binary and I'll get the binary equivalent of this character. So converting, which consists of only two digits, zeros, 0 and 1. The process typically involves repeated division by 2 and noting the remainders where this is an example. So we have three examples actually. The first one, if I want to convert the decimal number 13 in base 10 to a number that is in base 2, the first thing I want to do is to divide 13 by 2. Alright? So after dividing 13 by 2, I'm going to be getting 6 remainder 1. Okay, I will write down my remainder somewhere. Then I'll pick this quotient and divide by 2 again. After dividing by 2, I'm going to be getting 3 remainder 0. I'll keep this 0 somewhere. Then I'll take this quotient again and divide by 2, which is going to be giving me 1 remainder 1. I'll note my 1 somewhere. I'll pick up this quotient and I'll divide by 2 again. This time I'm going to be having 0 remainder 1. So my final result is going to be 1 1 0 1 base 2, and that is it. That is how to convert from decimal to binary. Then we have this other example over here, converting 25 to binary. So basically what we are going to be having is 25 divided by 2, I have 12 remainder 1. 12 divided by 2 again, I have 6 remainder 0. 6 divided by 2, and it goes on and on. When you are done, just all these remainders, pack them together, base 2, that will be your response. The same thing goes for this other one. Alright, so you can see 39 divided by 2, 19 divided by 2, 9 divided by 2, 4 divided by 2, and it goes on and on. So in each example, the binary representation is obtained by reading the remainders from bottom to top. Okay, from bottom like this to the top. So the remainders at each step are the binary digits, and the final binary representation is derived by arranging those digits in the correct order. Now, the next type of conversion that we're going to be looking at is the decimal fraction to binary fraction. So let's take for example, I have a decimal fraction 0.625. Um, the first thing I want to do is to multiply this number by 2 since I'm converting to binary. So I'll multiply it by 2 first, then I'll have 1.25. I'm going to note my integer part, then the fractional part. This fractional part, I'll multiply it by 2 in the next step. So after multiplying by 2, I'll get 0.5. Now, this is the integer part, which is 0, then the fractional part is 0.5. This fractional part, I will multiply it by 2 again to get 1.0. So when you are trying to derive the if when you are trying to convert from decimal fraction to binary fraction, if you encounter 1.0, it's a good place for you to truncate your computation. So your answer is going to be, the response is going to be, the result rather is going to be 1 0 1 to base 2. Okay, that is your output, your results. So for the second one, let's look at this one over here, 0.8. So for this 0.8 to base 10, if I want to convert it to base 2, just 0.8 multiplied by 2 first, I'll be getting 1.6. The first binary digit is 1, which is what I have over here, the whole number part. This is the fractional part, 0.6. This fractional part, I'll multiply it by 2 to get 1.2. So the whole number part is 1, the fractional part is 0.2. So don't forget that we are noting down the whole number part. So that fractional part, I'll multiply by 2 again to get 0.4. So the whole number part in this case is 0, the fractional part becomes 0.4. So the calculation continues like that. The calculation continues like that. So when you have gotten the number of precision that you want, you are going to stop. All right, you are going to stop. So your response, your output is going to be 0.110001, then whatsoever other result you are getting. So you can see 0.1100110011 and it continues like that. So that is for the second example. For the third example, I'm having zero point 0.3 for us to convert to binary digits. So I'll multiply by 2 first. This is the integer part and this is the whole number part. I'll multiply by 2 again. This is the integer part. This is the fractional part rather. I think I made a mistake here. This is the fractional part. This is the integer part. No, control Z. So in this other case, multiply by 2. I have the fractional part and the whole number part. In this case also, this is going to be the fractional, the whole number, and the computation continues like that until you get to your desired precision. So I rounded this one over to this one was rounded over to the over to 6 digits just for brevity. So we also have binary to decimal conversion. If you have a number in binary form, how do you convert it to a decimal? That is what we want to look at now. So if I have this number, for example, 101110 to base 2, how can I convert it to a decimal, a number in base 10? So the first thing you want to do is to line up all these numbers like this. You can see that I have from the beginning 1011110. So you're going to be writing everything 10111 and 0. So on the second part, you're going to be multiplying by 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to the power of 3, 4, and 5. For this first one, I'm having 32. This one, I'm having 0, 8, 4, 2, and 0. Then the next thing for you to do is just to add up all these ones. After adding them up, then you get your number in base 10. And that is it. It is pretty straightforward. So you do the same thing for this one. Just all these numbers over here 110, 1110. You can see 110, 1110. So multiply this last digit over here by 2 raised to the power of 0, this next one by 2 raised to the power of 1, the next one by 2 raised to the power of 2, and the list continues like that. Add up all these results and you get your number in base 10. So this is also one other example that you can use to toughen up. So that is it. So these examples, they demonstrate the process of converting binary numbers to decimal by multiplying each bit by the corresponding power of 2 and summing up the result. Up next, we're going to be talking about binary fraction to decimal fraction conversion. So if I have this binary fraction, for example, and I want to convert it to decimal, how will I go about it? So you see that I have 0.101. What I want to do is very simple. So I'll just multiply this one by 2 raised to power negative 1. That is what I'm having on this line over here. Okay. Then I'll multiply 0 by 2 raised to power negative 2. That is what I'm having over here. Then I'll multiply 1 by 2 raised to the power of negative 3. That is what I'm having over here. Okay. Just add 0.5 to this and you get your final solution. This is it over here. So for the second one, this extreme digit over here, multiply it by 2 raised to the power of negative 1, multiply this one by 2 raised to the power of negative 2, multiply this by 2 raised to the power of negative 3. Anything you get, just add everything up together and you have your output. Then the same thing goes for this third one. Okay. So these examples, they demonstrate the process of converting binary fractions to decimal fractions by multiplying each bit by the corresponding negative power of 2, all right, and summing up the result. So let's talk about briefly floating point number representation. So the floating point number is a real number representation such that the decimal number can be made to float across the digits of the number without changing the value of the number. For example, if I have 217.736, if this is a normal floating point number, I can represent this, if you remember your standard form very well, I can represent this as 2.17736 Then I'll bring in this e over here, then 2. This works in, I think, Python. So this works in, I believe Python has something like this. Yes. So basically, I'm shifting this decimal point 2 positions to my left. I'm shifting it backwards 1 2. That is the reason why I'm having 2 over here. All right. Then I'm shifting from this position, I'm shifting only 1 step backwards. That's why I'm having 1. But from this position, if I should move 2 steps forward, that's why I'm having negative 2 over here. So they are having the same representation. So for this second one, using the same trick can be applied in the binary system as well. In the binary system, the same trick can be applied in the binary system. For example, if I have this particular number over here and I'm saying multiplied by 2 raised to the power of negative 1, okay, if I should shift this back 1 step, this will be 2 raised to the power of 0. If I shift it like 2 steps backward again, this will be 2 raised to the power of 2. All right. So just note how you shift and how you add up the powers or subtract from the powers. So that is how you represent floating point numbers in your computer. Now, addition of binary numbers. If you want to add binary numbers, I think it's better I bring this up 1 step. So addition of binary numbers. If you want to add 2 binary numbers, for example, I have 1011 and I have 110. For me to add them together, this will be 1 plus 0. That will be giving me this one over here. So 1 plus 1 is going to be giving me, normally I should have 2 in base 10, but you know that this is binary. So I'm going to be carrying 1 over, alright? I'm going to be carrying 1 over to this particular column over here. So 1 plus 1, it will be giving me 1 0. I will write 0, I'll carry 1. Then after carrying 1, 1 plus 0 is 1. 1 plus 1 is going to be 2 normally, but this is base 2. So that will be 1 0 again. So I'll write my 0. Alright, then I'll carry 1 again. 1 plus 1 is going to be giving me 1 0. I'll write the 0 and I'll carry 1. So the 1 is what I'm having here. That is why I'm having 10001 as the answer over here. So that is how to add binary numbers together. So we also have what we refer to as the complement of a number. The complement of a number is an operation that involves changing the bits of a binary number. There are two commonly used complements. We have the ones complement and the nines complement. We also have the twos complement, but I'm going to be taking the ones complement and the nines complement here. In the ones complement, each bit in a binary number is inverted or flipped. The operation is performed by changing all the zeros to ones, then all the ones you change them to zero. For example, this is not supposed to be here. This is supposed to be like this. Yes, this is also supposed to be like this. Yes. So please bear with me. Yes. So the ones complement of 1011 is going to be 0101. Just change all the ones to zeros and all the zeros to ones. The same thing goes for this one. All right. So as for the nines complement is a variant used in the decimal system. To find the nines complement of a decimal number, subtract each digit from 9, and that is it. For example, the nines complement of 9, 5, and 6 is 543. The reason is because if you subtract 4 from 9, you get 5. If you subtract 5 from 9, you get 4. If you subtract 6 from 9, you will get 3. Alright, which is what I showed over here. So the uses of complement, we have negative number representation. In computing, the ones complement is often used to represent negative numbers. To represent negative numbers, the leftmost bit is reserved as the sign bit. If it is 1, then the number is negative, and if it is 0, the number is positive. We also have the error detection as well. Complements are used in error detection codes, such as the checksum in network protocols. Then we have subtraction. Complements are also used in subtraction operations by converting it to addition. So you can use the complement to convert a subtraction operation to addition, then you carry out your operation like that. Relationship between ones and twos complement. The two's complement of a binary number is obtained by adding 1 to the ones complement of the number. This representation allows for more efficient subtraction operations in computer systems. So basically, for you to find the two's complement, you look for the ones complement, then you add 1 to it, and that is all. So understanding complement is crucial in digital systems as it provides a way to represent negative numbers and facilitates operation like addition and subtraction. So once I wanted to demonstrate one's complement subtraction here. So I did the direct subtraction first, then to show you that this result is going to be the same as the complement subtraction. So if I want to subtract 1010 from 1111, this is what I would have. Okay. So if I want to do this subtraction, 1 minus 0 will give me 1. 1 minus 1 will give me 0, 1 minus 0 will give me 1, 1 minus 1 will give me 0 again. So this is what we are expecting to be the result. Alright. So don't forget, I'm subtracting this from this. Now, for us to use one's complement subtraction, you take the one's complement of the subtrahend. The subtrahend is this one, which you want to subtract from the other one. So take the one's complement of it by converting each bit, by inverting each bit. So basically, this is going to be 0, 1, 0, 1, which is what I have here. After that, add that one's complement of the subtrahend to the minuend. This is the minuend over here. This is the minuend over here. Then add the one's complement of this to this. So if you want to add it, so I brought this one over here. Okay. Then I brought that one's complement. I brought it down. The one's complement of this. I brought it down here. Now we have converted it to addition operation. If you remember what we said over here. Exactly. Complements are used in subtraction operations by converting it into addition. Okay, so with what I did over here, I've converted this operation to addition operation. So 1 plus 1 is going to be giving me 0, basically 1 0, but I carry 1. Carrying 1 to this end, 1 plus 1 is giving me 1 0, plus 0 again is still giving me 1 0. So I write down my 0, I carry 1. After carrying 1, 1 plus 1 is 1 0, plus 1 again, that will be 1 1. I write 1, I carry 1. 1 plus 1 is 1 0, plus 0 is also 1 0 again. I'll write the 0, then I can bring the 1 somewhere here. There is nothing to add anymore, so I brought the 1 down here. Now, if there is a carry after adding, add it to the result. This is the carry over here. Okay, this is the carry. This is 4 digits, and this is another 4 digits. So basically, this is the carry. So just bring the carry down to this place. Okay, then you add it to the result. So if after adding the carry, okay, yes, if there is a carry after adding, add it to the result. In our case, the number colored red is the carry, which is this one. So we take it and add it to the result. Taking it and adding it to the result, we are going to be having this. Don't forget, this is the result that we are having initially. We add our carry and we are going to be having 1 plus 0 will give me 1. Then we bring down the remaining ones. And if you check it very well, this is the same thing as using the direct substitution. So any carry from the leftmost bit, like if you have 1 at the beginning here, you can just discard it. So since there is no carry in our own case, you can leave the final answer as this. Alright. So that will be all for the conversion of numbers. The final thing that we're going to be talking about is binary coded decimals. So binary coded decimals is a binary representation of decimal numbers. In BCD, each decimal digit is represented by a fixed number of binary bits. Typically, each decimal digit is represented by 4 bits. Okay, and these 4 bits they are referred to as nibble. They are referred to as nibble. So as for the representation in binary coded decimal, each decimal digit is separately encoded into its binary equivalent. The range of values for each digit in BCD is this to this. For example, so 0 is going to be represented by 0000, 1 is going to be represented by 0001, Then 2 is going to be represented by 0010, just the same way you will count in binary. Copy this and let me make two more rows. So this is going to be 3 and this is going to be 4. So for the 3, I'm going to be having 1 1 because this is 1 1 0 1 1. So this is going to be 1 0 0. This is going to be 1 0 0 for 4. Then the decimal 9 is going to be 1 0 0 1 because 8 is going to be 1 0 0 0. Yes. So for example, if I want to represent 725 in binary coded decimal, the decimal 7 is going to be this. The decimal 2 is going to be this. The decimal 5 is going to be this. So guess what? I'll just bring the binary representation of 7, 2, and 5. Lo and behold, together is the representation of 725 in binary coded decimal. So advantages of the binary coded decimal. The first one is human readability because BCD is more human readable compared to pure binary representation since each group of 4 bits directly corresponds to a decimal digit. So we also have the ease of decimal arithmetic because the BCD simplifies decimal arithmetic operations in digital circuits, making it easier to perform addition, subtraction, and other arithmetic operations. So if we want to add two BCD numbers together, for example, 5 and 3, 5 in binary coded decimal is this because 4 is going to be 0100. So as for 3, this is what we have here if you remember very well for 3. Okay, 0011. So just bring the two together, add them together, and you get 8. No, Control Z. Add them together and you get 8. Okay, which is the result in BCD. So binary coded decimal is a very useful representation when decimal operations are required in digital systems, but it is less space efficient than pure binary representation. It strikes a balance between human readability and computational efficiency in certain applications. So that will be all for this tutorial. Thank you very much for staying till the end. We started by giving a brief introduction to information representation, how to classify our information. Then we spoke about representation of characters. We spoke about the ASCII, the EBCDIC. We also spoke about representation of numbers in the binary, the octal, the decimal, and the hexadecimal number systems. Then we have conversion of numbers from decimal to binary, decimal fraction to binary fraction, binary to decimal, binary fraction to decimal fraction. We spoke about floating point number representation and computer arithmetic. All right. Then we have the addition, the complementary subtraction, where I demonstrated the normal subtraction first. Then I spoke about the complementary subtraction. Then I spoke about binary coded decimal. Then I showed some comparison between the two of them, between pure binary and binary coded decimal. So thank you very much. If there's anything, any particular thing in this video that you don't understand or you need more clarification on, please, the comment section is open, so you can just drop your comments and I'll respond to it ASAP. Thank you very much. I'll see you in the next tutorial. Bye for now.